Question 2 from the 2018 free response part of the exam deals with a particle moving on the x-axis, and they're giving you the velocity functions. And this is a calculator active problem, so you can use your graphing calculator to do any derivatives and integrals and all that. And actually, the more complex functions like this one, they would expect you to use a calculator to find any derivatives or integrals. Okay. All right. So part A, and they give you the particle is at position x equals -5 at t equals 0. And they want to find, for part A, find the acceleration of the particle at time t equals 3. So let's go to our paper and we'll do the correct write-up on that. So the acceleration is the derivative of the velocity. So we would want to write v prime of 3, which is equivalent to a of 3, which will be about, okay, and we're going to put this into our graphing calculator. Okay, so I'm going to go to my graphing calculator and put this in. So I want to press y equals, and I want to put my velocity function in for y1. Okay, so I want to press alpha x to get the fraction bar, and then 10, and then sine, and then 0.4 t squared, which in this case t will be x, so 0.4 x squared. Then close the parenthesis. And then the denominator is t squared minus t. So x squared minus x, and then plus 3. Okay, and then what we'll do back on our home screen, okay, we'll press alpha window, because we want the derivative, okay, so number 3, and take the derivative with respect to x of our velocity function, which was stored in y1, and we want to do this at 3. Okay, so we get an answer of -2.118. Let's go back and let's record that on our paper. So we'll record this is -2.118. Okay, and then let's go to part B. So for part B, we want to find the position of the particle at time t equals 3. We know the position at t equals 0, it's -5, right? So we want to integrate this from 0 to 3, and we want to integrate the velocity function because that would give us the change in position, okay, or displacement, okay? So let's go to our paper and we'll write that up, and then we'll go to our graphing calculator. Okay, so for part B, if we integrate from 0 to 3 of v of t dt, I know this is going to be equivalent to x of 3, so the position on the x-axis at time 3 minus the position at time 0, okay? And if I move this over, right, I would have x of 0 plus the integral from 0 to 3 v of t dt. So we would have x of 3 is equal to x of 0 plus the integral from 0 to 3 v of t dt. And we know x of 0 from our paper that it is -5, right? So we would have x of 3 is equal to -5 plus the integral from 0 to 3 v of t dt. And we'll do this integral. We'll take -5 and we'll add the integral to it, and we'll have the position at time t equals 3. Because this is the change in position, okay? All right? So x of 3 is equal to, and we're going to go to our calculator and put that in. So we want to type in -5 and then plus, and then alpha window for the integration, number 4. And we want to integrate from 0 to 3. And our velocity function was stored as y1, so we want to press alpha trace y1 x and press enter, and we get -1.7602, so that would just be -1.760 or -1.76, and that's our answer to this. So I'm going to go back and record. Now, technically, I shouldn't be putting in equals here, okay? I should actually be so I'm going to change it, okay? They're not going to take off if you put it in equals, okay? But x of 3 is about -1.760. Okay, or -1.76 would be good too, because that'd be 3 decimal places. Okay, so that's the answer to part B. So for number 2C, okay, they want us to evaluate 0 to 3.5 v of t dt, and also evaluate 0 to 3.5 of the absolute value of v of t dt, and then interpret the meaning of each integral in the context of the problem, okay? So let's first evaluate these two integrals, okay? Let's do that first. And we'll go to our calculator, and actually, let's write it on our paper. So let's go to our paper, we'll write these two down, and then we'll go to our calculator. Okay, so what we want to do is we want to evaluate the integral from 0 to 3.5 v of t dt, and we want to know what that is. And then we also want to integrate 0 to 3.5 the absolute value of v of t dt. Now the absolute value of velocity is really speed, right? So this is integrating speed. So this one's going to give us total distance between 0 and 3.5. And this one's going to give us the displacement or the change in position, okay? So that's going to go into the interpretation of this, okay? So I'm going to go to my graphic calculator. I'm going to do both of these, okay? All right, so back to the graphing calculator. So we want to integrate, so we're going to press alpha window and number 4, and we're going to integrate from 0 to 3.5. And v of t, which we stored as y, so alpha trace number 1, and then dx. Okay, and then 2.844. Okay, and this is the change in position, which we call displacement when it's a particle moving, and we're using velocity and all that. Okay, now we want to do the absolute value of this. Okay, so again, we're going to integrate. So alpha window function integrate. So 0 to 3.5. But now we want to enter, before we put y1, we want to do the absolute value. So that's alpha window, and number 1 is the absolute value function, and then the absolute value of the velocity, which is stored in y1, and then dx. Okay, and we get 3.737. Okay, so let's go back to our paper and record these two values. So the integral from 0 to 3.5 of v of t dt, from the calculator, we got negative, or not negative, 2.844. So we'll record 2.844. You could also truncate, so it'd be 2.843. And then this one, okay, was 3.737. Okay, and then now we have to go into the meaning of these, okay? So what is this one? Okay, so this is the change in position, which we call displacement, okay, in physics. So the integral from 0 to 3.5 v of t dt is the displacement Now, instead of saying displacement, you could also say change in position, okay? Is the displacement of the particle between t equals 0 and t equals 3.5, okay? And I don't think they gave us units on this. No, they didn't. Okay, so just, you can't put units on this time, okay? You don't know if it's seconds or minutes, okay? Now, how about the absolute value ones? Okay, so what's this one? Okay, so 0 to 3.5, absolute value of v of t dt. Okay, so when we take the absolute value, that takes anything that's below the x-axis on the velocity and flip it up, right? So it's above the x-axis. So all of these function values have to be positive, right? So if we integrate, we accumulate distance, right? But in this case, all the velocities are going to be positive. So all our function heights are going to be positive, which is not going to give us the net change, but the total distance traveled, okay? So the integral from 0 to 3.5 of the absolute value of v of t dt is the total distance traveled by the particle between, and you got to add this part, between t equals 0 and t equals 3.5. Okay. Now you could write this as an integral, because when we say between, you could also, say this between, in this one and the previous one, you could say something like this: 0 less than or equal to t, which is less than or equal to 3.5. That's between 0 and 3.5 still. Okay. So I just realized you didn't see this. Okay. Let me take this off my pad. Okay. Sorry. So integral from 0 to 3.5 of absolute value of v of t dt is the total distance traveled by the particle between t equals 0 and t equals 3.5. So this between t equals 0 and t equals 3.5 could be written as an inequality like this, okay, for this one and for this one, okay? It wouldn't matter either way you write it, as long as it's on this time interval, okay, that you're writing that. So you can write it in words, or you could write it as inequality. You could even write it in interval notation, okay? So it'd be bracket 0, comma 3.5 bracket. Okay. Sorry, I didn't realize I was writing and you guys couldn't see it. Okay. All right. So let's go to part D now. Okay. So for part D, they're asking you a second particle moves along the x-axis with position given by this second function, right? So this is the position function, right? And it's equal to t squared minus t. And it's for 0 less than or equal to t, less than or equal to 3.5. So it only works for those between that time interval, okay? At what time t are the two particles moving with the same velocity, okay? So the velocities have to be the same. That would mean for this function right here, I'd have to find the velocity function for that particle for v sub 2 of t, okay? And then set it equal to this velocity function and see where they're equal. But I only want to look on a limited region, right? I only want to look between 0 and 3.5 to see if this is happening, okay? All right, so let's go to our paper. We'll write this up formally, and then we'll go to our graphing calculator to solve this, okay? Okay, so I know that x sub 2 of t, from what I read, was t squared minus t. Okay, so that would mean x prime sub 2 of t, which is also equivalent to v sub 2. Hold on, let me get some more ink. V sub 2, I had to change colors too. V sub 2 of t would be equal to 2t minus 1. Okay, all right, now I know this is v sub 2 of t, right? I want to know where these velocities are the same. So you need to write this, because you're going to solve this, okay? You're going to have v of t, which is the original velocity of the original particle, okay? And we want to know when this is equal to v sub 2 of t, right? Okay? So we have the velocity function. In this velocity function, we already have stored in our calculator y1. We're going to put this one in for y2, okay? And we're going to put in 2t minus 1, okay? And then we're going to look between 0 and 3.5 and see where they intersect. And that will give me the time or times in which the velocities are equivalent, okay, or the same. All right, let's go to our graphing calculator now. So from our graphing calculator, we want to go back to y equals and go down here to y2, and we want to type in the velocity function for that second particle, right? V sub 2, okay? And we're going to write 2x minus 1. Okay, and our window, we want to only look between 0 and 3.5. So 0 to 3.5. I would keep the x scale as 1. Y min to y max, who knows what this should be. Okay, so let's just keep it at negative 10 to 10. And then let's graph it and see what happens. Okay, so it looks like it's only going to happen right here. Okay, I'm going to do a zoom box. So I'm going to show you something. You wouldn't necessarily have to do this on this problem, okay? But I just want to show you a feature that you might want to use, okay? We're going to zoom box, and just to get a good window. Okay, I'm going to press enter there. I want to go above where they intersect at least, right? To the maximum. Actually, let's just go up a little bit higher. A little too high. And press, and then go to the right. And we can adjust this a little bit if we want to. I'm going to come down a little bit. And then I'm going to press enter. I just want to show you this, okay? You wouldn't have to do this. It's right here though, right? That's when the two velocities are the same, okay? So the red one is the velocity of particle 2, and the blue one's the velocity of the first particle, okay? So let's go to second, calc, and then number 5, intersect, and then enter, enter, and guess, just be close to it, and it's 1.57, and that 5 right in the fourth position, right, will cause this 0 to become a 1. So 1.571, okay? So let's go to our paper and let's record this value. So solving this equation that we have right here, t would be approximately 1.571. Okay, so the two particles are moving with the same velocity at time t equals 1.571, okay? The two particles have the same velocity at t is approximately 1.571, okay? And this whole problem was a particle moving on a line problem because it was moving on the x-axis, so that's just back and forth, right, on one line. Okay, so they're going to ask you a problem like this, okay? They may not, okay, for AB, they may not ask us the total distance because that's something that's going to come up in the unit after the exam that we're going to do, okay? So you probably won't see that, but you should know that the integral from 0 to 3.5 v of t is the displacement, okay? Because we've talked about that one, okay? And that's in earlier units. Okay, let's go to the next problem, guys. From the 2011 BC free response questions number 3, I want you to do this one, okay? So let fx equal e to the 2x, and then r is this region bounded in the first quadrant by the graph of f, which is this top part right here, okay? The coordinate axes, all right, which is the y-axis and the x-axis, and the vertical line x equals k is greater than 0, and then the region r is shown in the figure above, okay? Write, but do not evaluate an expression involving an integral that gives the perimeter of R in terms of K. Okay, so really the only one we really need the integral for is this curve part right here, right? Okay, and so we're gonna have to use arc length to find that, and that's a nice smooth curve. So we're gonna be able to do that, okay? This distance right here would be 1. The distance from here to here would be K, and then this vertical distance right here is the y coordinate here because that's how high above the x-axis. And that would be the same as this length. So that'd be e to the 2k, all right? Okay, so let's go ahead and go to part A on our paper and let's write this one out. Okay, so we wanna find this part right here, but to get that, we're gonna need to find the derivative of this. So I'm gonna call y equals e to the 2x, okay? So y is equal to e to the 2x, and then dy over dx would equal e to the 2x times 2, okay, or 2e to the 2x, okay? And then we're going to want to integrate that along that length, that horizontal from x equals 0 to x equals k, all right? So the perimeter would equal the integral from 0 to k of the square root of 1 plus, and it would be this amount right here. So 2e to the 2x, because that's your dy over dx, squared, and then dx, okay? Now that'd be that top part, okay? Then we need to add to that the left side, which would be 1, plus the bottom, and that'd be the distance from the origin to that vertical line k, so that'd be k, and then plus that vertical piece that I talked about, and it would be e to the 2k. And that would give you the perimeter of region R, okay? Let's go to part B. So for part B, the region R is rotated about the x-axis to form a solid. Find the volume V of the solid in terms of K, okay? So we're rotating around this x-axis, right? Okay, so we're gonna need, and there's no gap, okay? We're gonna go all the way to the function. So we're just gonna have one radius here, right? So this is gonna be a disk method, okay? So that's gonna be my radius R, okay? and that would be e to the 2k minus 0. Okay, that'd be my r. Okay, so I'm going to go to the paper and we'll write this one up. Okay, so my r, my radius, is going to be e to the 2x minus 0, or just e to the 2x. Okay, and so we're going to integrate this to find the volume. We're going to integrate from 0 to k of pi r squared dx. Okay, so pi times e to the 2x squared and then dx. That's your pi r squared. Okay, so that would give you the volume. Okay, all right, so then let's figure this out. Okay, so this would be the integral, because they want this in terms of k, right? You know what, I should have pulled the pi out. Let's pull the pi out. Okay, and we integrate from 0 to k, and then we're going to multiply these exponents because that's exponents rule. So that'd be e to the 4x and then dx. Okay, and this is going to be fairly easy to integrate. Okay, so we're going to let u equal 4x, and then du, and some of you might not need to do this. Okay, and that's fine. U is 4x, du is 4dx. I actually do this just to make sure I'm getting everything right. Okay, so we need a 4, so I also need to multiply by 1/4. Okay, or divide this pi by 4. Okay, so this would be pi over 4, the integral from 0 to k of 4 e to the 4x dx. Okay, so I'm going to change this to u values. I'm going to slide this up a little bit too. Okay, so this is pi over 4. Now I'm going to change everything to u's. Okay, so u, when x is 0, u would be 0. And when x is k, u would be 4k. 4k. And then we have e to the u du. And now we can integrate this. Okay, so this would be pi over 4. And the integral of e to the u is just simply e to the u. Okay, so e to the u evaluated from 0 to 4k. Okay, so that'd be pi over, I'm going to come to the side, pi over 4, okay, e to the 4k minus pi over 4 e to the 0. But e to the 0 is going to be 1, okay? So in terms of k, all right, it would be pi over 4 e to the 4k minus pi over 4. Or if you wanted to, okay, and I would stop there. I mean, that's it, okay? You could factor out a pi over 4, and then it would be e to the 4k minus 1. Okay, so that's the volume of this region that they're talking about. Okay, so let's go to part C. So for part C, the volume V found in part B changes as k changes. Okay, if dk over dt is equal to 1/3, determine dv dt when k equals 1/2. Okay, all right, so let's go to our paper and let's do this one. All right, so I'm going to write down some things we know. We know that dk over dt over dt is equal to 1/3, okay? And we want to find dv dt when k is equal to 1/2. Now we also have v, right? So what was v? V was pi over 4, and I'm getting that from part B. Okay, pi over 4 e to the 4k, and then minus pi over 4. Okay, so all I need to do is take the derivative with respect to time. Now, what am I going to pick up on this left-hand side? I'm going to pick up dv dt. Over here on this right-hand side, because it's in terms of k, I'm going to also pick up a dk dt, right? And that's why we need this dk over dt is equal to 1/3, okay? All right, so if I take the derivative with respect to time of both sides, okay, so this left-hand side becomes dv dt, okay? The derivative with respect to time of pi over 4 e to the 4k, well, this is a constant, so that'd be pi over 4, okay? And the derivative of e to the 4k would be e to the 4k times, and the derivative of 4k would be 4 dk over dt minus this is a constant, so the derivative of that would just be 0. So I wouldn't really need that, right? So then that would mean dv over dt, and we can clean this up a little bit before we plug everything in, because I'm multiplying by pi over 4, but here I'm multiplying by 4, so my 4s are going to cancel, and so I'm left with pi e to the 4k, all right, and then times dk over dt, and now I can plug everything in, okay? So dv or dt is equal to pi e to the 4, and my k, when I want to do this, k is going to be 1/2, so 4 times 1/2, and then times my dk over dt, which is 1/3, or what did I write 2? 1/3, right? I know I wrote 2 because I wrote 1/2 for just a minute ago, right? So 1/3. Okay, so half of 4 is 2, so this is pi e squared. So dv, the final answer would be dv over dt is equal to pi e squared over 3. And that's the rate at which the volume is increasing. I'll slide it up so you can read it. Okay, so that's the rate at which the volume is increasing. Okay, so the volume is increasing pi e squared over 3, okay, when k equals 1/2. Okay? When I gotta laugh at myself. All right, so when, you can laugh at me too. All right, so when k equals 1/2. All right, and that's the answer to part C.